Dr. Pradip Kalbar is civil environmental engineer and was awarded PhD from Indian Institute of Technology, Bombay. His PhD thesis received Excellence in PhD Thesis Award 2014 from IIT Bombay. Presently, he works as Associate Professor at Center for Urban Science and Engineering at IIT B. Dr. Kalbar's area of research includes water supply and wastewater treatment. He was a member of the Technical Advisory Committee for Water Supply of Municipal Corporation of Greater Mumbai and is an elected member of the Government Committee of International Water Association Specialist Group on Intermittent Water Supply. He is editor of reputed international journal Water Use, published by IWA. Recently, interventions based on his work for improving water supply in India are recommended by the Ministry of Jal Shakti for implementation in all the states. He works as advisor to various state governments in India on the matter of water supply and sewage. Dr. Kalbar has authored 4 book chapters and published several scientific papers in peer-reviewed international journals and conferences. He also had wide industrial and consulting experience in the area of water sector, urban wastewater management and environmental sustainability.
Okay, so welcome to this webinar series on water for public health, preparing for disaster and pandemics. So we have this is organized by NIH Roorkee and which is a collaborating institute for us in our research project funded by Department of Science and Technology. So this is I'm going to talk about circular economy in water and sanitation sector and public health programs. So circular economy is a new emerging framework that is very useful for delivering water and sanitation services. So I work in Center for Urban Science Engineering at IIT Bombay. So first let us understand the urban water cycle. So water cycle is typically natural water cycle is always connected. So we abstract the water, treat the water, distribute, consume. Then there is a wastewater treatment plant, and then there is a disposal. So this is our urban water cycle. That is how is we are doing. But currently, what is happening is a lot of urbanization and different stresses are there, which are causing impact, and this cycle is linear. That means we are abstracting, treating, distributing, consuming, and again treating and disposing of. But there is no recycle or reuse is happening. Okay, so we are polluting the water systematically. So it is very important to have a circular economy approach in urban water cycle. And there are strategies to implement circular economy in water. So in this particular presentation, I will be talking about reducing first of all the consumption, reclaiming, recycling, reusing, recovering, and restoring the water in different forms in different sectors that we come across. So first, let us take a look at sewage generation and treatment. And this is very recent data which for across the states, you can see all the states are polluting, generating a lot of sewage, and which is polluting rivers and lakes. And we have a treatment gap. Some states have little bit trying to push a lot to create a sewage treatment infrastructure, and some states are lagging. For example, West Bengal, Kerala, and Bihar. These are the states which are lagging, and some states are going further, but still the gap is huge. So across India, on an average, there is a 30% sewage treatment capacity. So that is the challenge we have, that we have a huge treatment capacity gap. So water is an important resource, but generated wastewater is a more important resource. That means we always talk about the fresh water, but wastewater generated is more important because it also has a carbon capacity to generate energy. There is a nitrogen, there is a phosphorus. So there are many of these nutrients and resources are there. So it's a very important resource. So if you see the installation capacity, so we have number of STPs across India, 1600, around 1600, and that will be around 37,000 million or 38,000 million liters per day treatment capacity installed. Out of that, operational STPs are only 1,000, around 1,100, and operational treatment capacity is around 26,000 or 27,000 million liters per day. So we also have a problem with the utilization, because many times treatment plants are installed without thinking whether there is a feeding network available, whether there is a sewage collection is happening or not. So enthusiastically people install the sewage treatment plant without uh, considering the other sanitation aspects of whether people are using toilets, whether people are connected with the sewerage system or not. So capacity utilization of the entire infrastructure in water sector is a big challenge. Okay. So so what happens is we have to treat the sewage, untreated grey water or the sewage, to some treatment standard. So historically we have been following this Schedule 6, which is coming from Environment Protection Act 1986, where we have been given this particular guidelines that we have to treat the water for 30 milligram per liter. And if there is a public sewers, and municipality will have a sewage treatment plant, and they will again treat it back to 30 milligram per liter, so that it can be disposed of in lakes and rivers. But the problem is, historically we have uh, uh, these guidelines, but our lakes and rivers are still polluted even with these standards. So a lot of public interest litigation, a lot of cases have been filed in Honorable Supreme Court, and then they have also now Honorable National Green Tribunal, which is taking the cognizance of these cases and the files. So these standards were challenged many times. Okay, that whether 30 milligram per liter is used will be sufficient for maintaining the good water quality or not in the systems. So we have the then desired water quality for recycle also. So this was for treatment, but if you want to recycle, we are also very ahead in terms of putting the norms. For example, in Mumbai in 2005, very stringent norms were laid, even more stringent than US and other countries, developed countries. For example, you can see BOD expected for recycled water was less than 5, and total coliform less than 2 carcinogenic contaminations. So basically, this water can be used for toilet flushing, landscape irrigation, fire protection system, and air conditioning. Because our cities and metros having a lot of water resource stress, and with the newer challenges such as pandemics, disasters, and climate change, our water resources will be always challenging. So this was a thought given that all the high-rise buildings that are 21 story and above will have a recycling of sewage. However, if you see, the challenge is how we can enforce it, because enforcement in India is not that much done very properly. So still, although the norms are there, but in implementation is a big challenge. Now, as I said, Honorable National Green Tribunal has taken the cognizance of the PILs that have been filed, and there was a lot of deliberation committees, and then they have issued the order in 2019, 30th April 2019, that the CV is to be treated will have this kind of standard. So this was the committee recommendation to the NGT, that in metro cities like Mumbai, Chennai, Delhi, Hyderabad, you have BOD of less than 10 milligram per liter, okay, for discharge in the ambient water sources such as lakes and rivers. For class 1 cities, that means population having 1 lakh and above, it is 20 milligram per liter, and for other tier 2 cities, class 2 cities, or the emerging towns, rural areas, it is 30 milligram per liter. Now, what has happened is, what they have said is uh, uh, all water resources are same, and uh, we cannot differentiate between rural and urban areas. Okay, so there are these are applicable to all the cases. So this is the recent order issued by National Green Tribunal. Now this poses two challenges. One is that all this, like I told you, 37% is the established sewage treatment capacity. Those are for 30 milligram per liter discharge standards. Now all those 37%, around 26,000 million liters per day, or 37,000 million liters per day, has to be upgraded to 10 milligram per liter standard. Right. So that is a one big challenge for us. And then also filling the gap of the remaining infrastructure of about remaining 63% capacity to be installed in coming years. It has to be also on this 10 milligram per liter, right? So basically you are our local bodies, state governments need huge funding, huge support for creating this infrastructure. So we need a very different approaches for wastewater management to achieve these targets, to respond to these disasters, pandemics, new regulations. So let us understand the prevention and conservation side of the wastewater management. So first, we have to uh, educate our people, citizens, about reducing the consumption, putting the efficient devices, because that is the major role it will play in terms of reducing the stress on the fresh water. If we are not working on this and only talking about treatment, we will never able to catch up the problem. Okay, so that is one big arm that we have to work. And then you talk about it, treatment, recycling, or recovery. So we have to start with treatment, but now we have reached to the stage where investing only on the treatment is not possible, because if you ask any urban local body to generate a funds for installing treatment capacity, even if somebody is funding, let's say World Bank, state government, central government, or any other uh, 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 organization is funding the capital investment, the operational cost itself is not able to cope up by urban local bodies. So we have to make this treatment side as a revenue side. So we have to recycle and recover, and the policies and the guidelines around that needs to be developed. Okay, so we have the household or building level treatment, we have decentralized treatment system, we have a centralized treatment system. So all levels this can be implemented and has to be implemented to make the circular economy possible. Coming to the treatment side, and this module is very introductory on treatment side, and you can refer to the other literature or the videos. But you can see there are a number of technologies. There is no dearth of technology for treating any kind of wastewater, whether it is domestic or industrial. So we have physical chemical, we have biological, we have aerobic, we have anaerobic, right? So there are many of these kind of treatment systems available. Uh, Aerobic, suspended growth, attached growth, USB anaerobic systems are there. Number of I cannot name all this, but technology is not issue. Just remember that is the one key message that I want to give. Okay, number of technologies are there. Then what is the challenge? So the challenge, or what is currently wrong in the current approach, is we are having the cities, which is there are number of households which are consuming the water from far-fetched reservoirs. The reservoirs are, for example, for Mumbai, it is 100 kilometers, 200 kilometers from where water is coming. Then we are consuming detergents and chemicals in the houses. We are consuming food in the houses. All that is consumed, and we are discharging wastewater, and which is generated through feces and other bathroom and kitchens and kitchen and other washings of floors. All that is contributing as a wastewater. Now, what we are doing historically is creating a centralized treatment systems and trying to treat. So now again, the treatment network has to be laid, a lot of investment has to go in. And again, the operating this plant has not been very successful. Many locations I see the plants are not operating properly. So what is happening? The pollutants are getting escaped in the effluent or in the sludge form. Okay, so we are at a loss. Now, additionally, what we are doing is we are putting the food which is produced using these artificial fertilizers such as urea or diammonium phosphate. So what is happening? We are fixing nitrogen with huge amount of energy, which is again producing carbon dioxide, and that is paid by energy resources, right? So huge amount of energy sector is also associated with this particular problem of providing food to us, or these are detergents or chemicals also. Now, and in the centralized wastewater treatment, we are again putting back the energy to take out this nitrogen. So we are fixing the nitrogen, we are consuming the nitrogen, and again we are putting energy. So it is not a sustainable loop, right? You can imagine this is very simple. It is not a sustainable loop. So we have to first stop the consuming the artificial fertilizers, then creating a fertilizer loop from the sludge or the other recovery mechanisms, and again giving back to the agriculture. And we have to stop consuming this water from the fresh reservoirs, and we have to create our own water from the cities itself, okay, for secondary purposes, and that is for industries or commercials. So this is that also the energy required for the treatment system has to be minimized, and this all is possible required, and it is possible because of decentralization. So if you decentralize the systems, if you use some very different models in the cities and the rural areas, we can do it. We have to make the consumers aware. So let us discuss how this can be achieved. So centralized meaning that everything taken out of the area and treated and then again put back to the, if recycling is aimed. So that becomes very costly. If you have a decentralized system like this, where you collect the entire system and only by neighborhood level or the some community level you treat the water, and again recycling is then the more recycling opportunities can be created for decentralized treatment in a facility. The issue is two small systems will be difficult to operate. So we don't have to go for a very small like household level or building level, because those are very difficult to operate systems. So it has to be some appropriate scale. Okay, so and it do not offer scale of economy, right? So if you have a very small systems, all system will not be synchronized, their scale of economy will not be there. On the other hand, if you create a very highly centralized system, place another challenges in recycling of treated effluent and sludge, because at some other because after some point it will not offer any scale of economy, okay, beyond one point. So we have to keep these 2 points in mind and then plan our infrastructure, sanitation infrastructure. So this particular centralized systems additionally require deeper sewerage network for flat terrain and difficult to maintain. So you have highly decentralized or highly centralized systems. Current comfort zone of consultants, state governments, and many stakeholders is to have highly centralized systems. One DPR they want to have and solve the problem, but that is not possible. That is not working well. Other hand, people directly promote highly decentralized systems where you have only very small building level or household level, which is also not sustainable. The ideal zone for achieving 6 Rs, that is circular economy through the 6 Rs principle that I talked about, is possible when you have ideal scale for the given location depending on the population density, depending on the topography. So that knowledge has to be taken into consideration when you plan a sanitation infrastructure. So what are the wastewater recycling challenges? One is scale of implementation is not known. It has to be determined for every case, that as I said in the previous slide. Energy requirement, can we make it energy neutral? Because we have to make the system energy neutral. Other resources, nitrogen and phosphorus, can we close the loop? We have to work on not only the treatment slide, but we have to close the loop. Pathogens, because if you say many times people talk the toilet to tap, it's very currently we are not ready, our infrastructure is not ready, our capacity building is poor. So because the risks are very high if you just create a water for human touch. Emerging contaminants, household chemicals, many. So these are the very big challenges that we are having. Revenue models, who will maintain this treatment system? So we need a innovative revenue models. Operation and maintenance challenges, urban local building capacity building and governance. So huge challenges are there, and conservation is a key, consumer demand management and reduction in generation. So these are the key issues that we are facing in wastewater recycling. So these all I have documented in my research group. We have this publication where we have documented this for our country. So review of circular economy in urban water. So what we have proposed is, we have natural environment, we have water treatment plant, we have urban areas, we have wastewater treatment plant, we have industries and agricultural land. So basically this is our system boundary for water, and water get exchanged between these sectors, right? So and then the wastewater is getting generated, and treated wastewater is disposed of without recycle or use. So what we are proposing is, we apply reduce, reuse, recycle, reclaim, recover and restore these principles to put back the this particular water in the other loops. Okay, so from moving from linear economy to circular economy. So how we can do that is, basically first we have to talk about reducing the water in each sector. Then reusing, that industries can create a cascading of reused water in urban areas. Water can be used for secondary purposes. Then recycle, you treat the water and again take back water for gardening, air conditioning, toilet flushing. You reclaim, the industries can reclaim the water from the cities, that is reclamation. restore excess recycled water, good quality water can be used for groundwater recharge and restoring, and recover. Then we recover the energy from the sludge, carbon, nitrogen, phosphorus. These are the resources that we can extract. So we have to make a confluence of these 6 R's with principles of circular economy and water as given by British standards. So these are the six strategies of 6 R's, and these are the principles of systems thinking. We have to think in systems. Value optimization for every step. Value optimization has to be taken into account. Innovation, collaboration, stewardship, and transparency of data. How much water is consumed. So a lot of data issues we have in India. So we have tabulated this for just for an M1 exercise, and many other experts can contribute to this. For example, optimal utilization of fresh water by using efficient fixtures, innovative practices, policy changes, transparency of data between the urban local body and the industry, cascading water consumer and water utilities. So basically, number of ideas can be put in to fulfill this table. And we have given one thought, but there can be many other thoughts that can contribute to this particular idea. And with the collaboration with NIH and other partners in our IC EcoWS project, we are working on developing technology packages for various different cases across India. For example, for building scale in dense urban context, what can happen is there can be number of technology options. For example, sequencing batch reactor, MBR or FBR or membrane bioreactor, which may some of the technologies may need further polishing, further treatment for effluent for using for toilet flushing or many other purposes. So many mechanized treatment systems are available. Okay, and this is one of the picture, one of the case study that you can remember, where MBR is placed in the basement and if water is used for different purposes. If land is available, we can make use of natural treatment systems such as constructed wetlands, as shown here, where septic tank is here and water is just applied to these plants and at the periphery of the compound. And this also works for this wherever land is available. So whole issue is urban local bodies have to plan this very upfront when they are planning expanded areas, when they are developing the new societies, new housing societies. And there can be community scale solutions using stabilization ponds, ductile ponds, and number of case studies are there across India. And the reference I have given here, you can refer to these documents where number of such resources are available. So the whole challenge we have is for a different conditions, different settings, how to choose the technology, for example, from SBR, from active sludge process, from MBR, from USB, and constructed wetland. Each of these technology provides unique challenge. So some technologies may produce water that is for useful for disposal or land irrigation. You can make some polishing treatment and make use for high grade applications. The whole challenge is the energy consumption we have to take into account, the capital cost, operation and maintenance cost we have to take into account, the reliability and durability of the treatment system we have to take into account, and the land requirement. So number of these issues are there which we have to consider when we take decision. So if you compare the mechanized treatment system and natural treatment system, there is a trade-off. For example, the mechanized treatment system has higher energy consumption but very low land requirement. Natural treatment systems such as constructed wetland we do not have energy consumption but requires a lot of land. So there is a trade-off, okay, for choosing the technology system. So the challenge is mechanized treatment systems are more intensive, as I said, but requires less land. And considering the gap in the treatment in India and progressive regulations, there is a need for installing new sewage treatment plants as well as the augmenting the existing. So I remember that there is a two challenge we are facing, augmentation and the installing new capacity. In either case, the challenge for Indian cities will be to achieve the cost-effective treatment, right? So cities, what they are looking for is a very sustainable, self-sustainable solution. Many projects have failed because somebody is coming funding the capital investment, but there is no operation and maintenance taken care properly. So the capital expenditure usually can be arranged from several funding modes. However, the constraints such as operational maintenance cost and land requirement limits the use of all variety of technologies available. Okay, so we have to focus the solution technology selection based on the operation and maintenance. Capex can be managed, can be developed in one go. The major headache for cities or for rural areas to maintain the treatment system for next 30-40 years for longer duration of time. If you take the cost issue, O&M cost issue now in the mind, so on this one analysis that we have done, on x-axis we have the outlet BOD, and y-axis we have operation and maintenance cost. So here you can see the mechanized treatment system costs are very high because the energy costs are very high. The energy required for aeration and other mechanized treatment is very high, whereas natural treatment system have very low operation and maintenance cost. And the outlet, this particular land requirement for variety of treatment levels. So on x-axis this is treatment level starting from, let's say, 150 to 5 milligram per liter at the outlet BOD. And inlet BOD assumed in this analysis is 300 milligram per liter after primary and then the primary treatment is there. So what is the land requirement is very high for natural treatment system. You can see the constructed wetland. This green one are shallow bed, and this pink one are the deep bed wetlands. So even with the deep bed, you need a lot of land. Okay, so that is the challenge. So we have to make a confluence of these two technologies, and that's where this shows that 30 milligram per liter we should shift to constructed wetlands, because after 30 milligram per liter major chunk was taken care by mechanized treatment system in a very low land requirement, and then we can move on to the constructed wetland so that remaining BOD load can be taken by this particular constructed wetland. So this hybrid treatment system is proposed as one of the solution, and where we, as said, we move from mechanized treatment system to natural treatment system, and this will create a long-term sustainability because your operation and maintenance costs are very low. So you start with 300 milligram liter, do a primary treatment, then your inlet maybe 210. So this configuration of this mechanism primary treatment will be varying for different input value. If BOD is very low, then we can do away only with anaerobic filter or some very simple treatment system. We do not even need a mechanized treatment system before going for natural treatment system. So if you make a hybrid treatment system, and which is shown here as a blue, you can see the operation and maintenance cost is come down. Okay, and here the land requirement also here for hybrid treatment system, the land requirement is lower than the natural treatment system. Okay, so this is how we can achieve the more sustainable solution. And in this one table I have given you for different treatment levels of 30, 10 and 5 milligram per liter. If you go for mechanized treatment system, if you go for mechanized treatment system followed by shallow bed, if you go for mechanized treatment system followed by shallow bed constructed wetland, this is the given land requirement, operation and maintenance cost. Okay, for this is for hybrid treatment system 1, and this is for hybrid treatment system 2. So this is one analysis that I have given, and it is published. You can search for hybrid treatment system, you will find the paper which is published in Journal of Clean Technologies and Policy. So what are the additional benefits of hybrid treatment system? It is not only the O&M cost, because if you propose hybrid treatment system to be implemented throughout India, total annual energy saving of about 200 gigawatt of energy in the existing STPs, and 340 gigawatt in the upcoming STPs will be there because of installation of this particular hybrid treatment system, because you are saving on operational energy. Additionally, there will be associated reduction in CO2 emissions, because you are not using the electricity from the grid, which is now coal fed. Around 60 to 70% energy is coming from thermal energy. So your CO2 emissions will be also reduced. So it will help in climate change and other sustainable development goals. So the HTS approach, hybrid treatment system approach, can easily be implemented in the around 400 cities in India, having population between 0.1 to, let's say, 10 lakhs, with cumulative population of about 200 million in the around 7,400 towns. So a lot of scope and potential is there. For the 53 cities having population of million plus, adoption of HTS approach is possible for STPs located outskirts of the city or decentralized infrastructure approach can also be adopted. The another very important benefit of HTS approach is HTS develops an opportunity to extract the resources such as water, energy, and materials. Because you see, you are now using microorganisms and the plants, algae, which can also be used as a natural treatment system, and fertilizers, bioplastics, metals, proteins, and building materials can be derived using the creating a value chain. As I told, value optimization is one of the circular economy principle, and this can be done using hybrid treatment system. If we stick to mechanized treatment system, we will not able to solve this problem. So implementation of hybrid treatment system also enhances regional job creation by encouraging small and medium enterprises. Because we are avoiding mechanized treatment system, hybrid treatment systems give a boost to the local economy. Hence, it is a more suitable for Make in India or Atmanirbhar Mission. This whatever initiatives central government has, it will support to that. So the way forward is the rural, peri-urban or urban areas first attempt should be made to make happen the treatment using constructed wetland directly after primary treatment. If this is not possible due to availability of land, then only any suitable HTS approach should be adopted. So the constructed wetlands are more suitable for Indian conditions from the available set of natural treatment system, and there is a lot of literature about it. The use of constructed wetland enables sustainable wastewater treatment and recycling, as it is not only useful for efficient organic load, but the nutrient removal efficiencies, the pathogen removal efficiencies are also very good. So with a very low cost, you are getting very good efficiencies. So constructed wetlands, which is a phytoremediation based technology, has a potential to remove emerging contaminant effectively. So in summary, there is no immediate need for toiletry tap, enough other avenues for recycling. So first we have to develop a practice of recycling using this hybrid treatment kind of treatment system paradigm. Recycling at the point of use, because if you take the sewage out of the boundary of the habitation and again trying to create a recycling network, it is very costly and not feasible. So recycling at the point of use or sale is very important. Scale of implementation of the solution is more important than the solution itself, because if you create a very highly centralized system, nobody is going to do anything with that. It will become a white elephant and very difficult to operate and maintain. So recycle water market need to be created in hand with recycling stations. Okay, so we have to work on creating a recycling market, changing the policies, changing the guidelines, changing the bylaws, and decentralization, closing the water, carbon, nitrogen, phosphorus, and energy loops is the key to achieve the sustainable wastewater management. And the entire this hybrid treatment system approach that I have presented will help in achieving the sustainable water infrastructure and water and sanitation infrastructure. Thank you.